This is the first video for lesson 8.2. 8.2 is all about graphing exponential functions. We started to learn about exponential functions in 8.1 when we compared them to linear and quadratics. Today we're going to go more in depth and look at how we graph them and how we transform those graphs. So how we shift the graphs left, right, up, down, and stretch and shrink them. Friday, we will be having a quiz on this material, so make sure that you post questions on Edmodo if you're not going to be in class, so you get those answered before you come back to class. Okay, so in this unit, we are going to be studying exponential and logarithmic functions. They are both widely used to describe economic and physical phenomena, such as compound interest, which we'll learn about in our next lesson, population growth, memory retention, decay of radioactive material. Think of radioactive material is found in like the atomic bomb, things like that. Measuring earthquakes and measuring pH. There are many careers that use exponential and logarithmic functions, including astronomers, archaeologists, psychologists, forensic scientists, the list goes on. So we are just going to be looking actually at exponential growth today, not logarithmic. That will come later in our unit. So a quick review on vocabulary. If we have an equation y equals b to the x, b is called the base, and x is our exponent. So we'll be referring to bases and exponents throughout the lesson. You will also see the letter e being used. E is not a variable, it is a constant. The value, well, it's a rational, but the value rounded to 5 digits is about 2.71828. It's called the natural base E, or Euler's number. This constant was discovered by Bernoulli when studying compound interest, which we're going to get to study in our next lesson. So you can read a little bit more about that, but if you see the letter E, know that we're talking about an irrational number that's about 2.71828. All right, let's go to our first example. Graphing the general form b to the x. So we've got two examples here, 2 to the x and 3 to the x. We're going to start with an exponent of 0. If I have 2 to the 0, we know anything to the 0 power is 1. So over here, 3 to the 0 will also be 1. 2 to the first power is 2. 2 squared is 2 times 2, which is 4. 2 cubed, 2 times 2 times 2 is 8. And if we have 3 to the first, that's 3. 3 squared, 9. 3 cubed is 27. Now let's think about negative exponents. If we have 2 to the negative 1, we know negative exponents create a reciprocal. So this becomes 1/2. 2 to the negative 2 is equal to 1 over 2 squared, which is 1/4. 3 to the x works similarly, so 3 to the negative 2 is equal to 1 over 3 squared, because that negative exponent moves the base into the denominator, or creates a reciprocal, and this is 1 over 9. If we have 3 to the negative 1, we have 1 over 3. Okay, so in your notes, you should have graph paper here. I'm going to go to the next page on the screen to graph these, but you should graph it right on that page in your notes. So I'm going to graph 2 to the x first. We know 2 to the 0 is 1, so I can put a point at 0, 1, then 1, 2, 2, 4, 3, 8, so 5, 6, 7, 8. And at negative 1, the output was 1/2. Oops, 1/2. And at negative 2, it was 1/4. So this graph looks roughly, well, this is not going to go very well with a stylus. Oops, your graph should look a lot nicer. It's going to look something roughly like that. Ooh, this is really rough. Okay, something like that. Notice it looks like it's never going to touch 0. Can you think of 2 to any power that would make this equal to 0? No, this can never be equal to 0. So it's never going to cross the horizontal axis here. So what do we call it when we have something that can't be crossed? An asymptote. Asymptotes also describe end behavior, and this is headed towards the end of the graph, towards infinity. We'll come back to that in a second. Let's graph 3 to the x. So 3 to the 0 we said was 1. Then 3 to the first is 3. 3 squared is 9. And we've got 1/3, so here it comes below the other graph. And then 1/27 ends up down here. So here it's below the other one, and then it crosses to be above. So that was 3 to the x. This one was 2 to the x. Okay, so let's go back to our notes. The domain for both of those functions, well, it's all real numbers. There are no breaks in the graph. It goes on forever in both directions. The range, the lowest value is 0, and we never hit that value. So our range would be 0, and our graphs keep going up and up towards infinity. Our y-intercept in both cases was 0, 1. Was it increasing or decreasing? Well, since we move left to right, this graph is increasing the whole time. Horizontal asymptote, y equals 0. That's the x-axis. End behavior, so as x goes to negative infinity, what's happening to f of x? What's happening to our graph? Well, our graph is going towards 0. So it's approaching the value of 0. As x goes to positive infinity, so as the graph moves to the right, what is our function doing? It's headed towards positive infinity. So we know, here's a rough sketch, our graphs are going towards 0 as we move to the left, and they're going up towards infinity as we move to the right. Key points. There are 2 key points we want to be thinking about. One is the y-intercept, so that's 0, 1. The other one is at x equals 1. Your key point there is always going to be 1, whatever your b value is. So it could be 1, 2, or it might be 1, 3, depending on the graph that you're looking at, or 1, 4 if your base was 4. Okay, so how does the value of b when b is greater than 1 affect the graph? Well, we're comparing 2 to the x and 3 to the x. b is your 2 or your 3. When we look at 3 to the x, this larger b value means that our rate of change is increasing more rapidly. It's changing faster. So here the graph is getting larger, the y values get larger and larger. Here they get smaller and smaller. So a larger b value, or we could say the larger the b value, the larger the b value, the greater the rate of change. So the slope is going to change more rapidly. What does the b value not affect? Well, it doesn't seem to affect the horizontal asymptote or end behavior. I'm just going to abbreviate EB for end behavior. It doesn't seem to affect the y-intercept or the domain or range. Okay, on to our next graph. All right, example 2, b to the x plus k. So we're going to look at 2 to the x plus 3 and 2 to the x minus 3. So we can think of these as 2 to the negative 2 plus 3, 2 to the negative 1 plus 3, 2 to the 0 plus 3, 2 to the 1, 2 to the 2, 2 cubed, plus 3. All right, so we actually know all of the values in this column right here, and then we're just adding 3 to them. We're taking the graph we had before and adding 3, essentially. So we have 1/4, 3 plus 1/4. I'm just going to leave that as 3 1/4. Then we have 3 1/2, because we know 2 to the negative 1 is 1/2. Then we have 1 plus 3, which is 4. We have 2 plus 3, which is 5. We have 4 plus 3, which is 7. And we have 8 plus 3, which is 11. Here we have 2 to the negative 2 minus 3. Well, that's 1/4 minus 3. And we have 2 to the negative 1, or 1/2 minus 3. We have 2 to the 0, which is 1 minus 3, 2 minus 3, 4 minus 3, 8 minus 3. Okay, so 1/4 minus 3 becomes negative 2 and 3/4. This is negative 2.5, negative 2, negative 1, 1, and 5. Okay, so let's graph that and see what that looks like. You're going to graph that here. I'm going to go to graph paper on the next page. So I had 3.25. So let's put that dot, oops, for negative 2. Negative 2 and 3 1/4. Then negative 1, 3.5. Then 0, 4. Let's reset. Okay, 4. Then 1, 5. 2, 7. And then after that it goes off the graph. So it's going to go up like this. Okay, so what happens after x equals negative 2? Well, these values keep getting smaller, but they don't cross the horizontal asymptote, which has moved up to 3. Why don't they cross it? Well, we have 2 to the x plus 3. No matter what x is, the smallest this can be is 1 over 2 to some really big number. So this is going to end up being something like 0.00000005 plus 3. So we get really, really close to 3, but we don't actually ever get to 3. Okay, so that was 2 to the x plus 3. Let's do 2 to the x minus 3. So at negative 2, we have negative 2 3/4. That's about there. Negative 1, negative 2.5. Then negative 2, negative 1, 1, and 5. So 3, 1, 2, 3, 4, 5. All right. There we go. And as we go to the left, this gets really close to negative 3. So negative 3 is your new horizontal asymptote for this one. And this was 2 to the x minus 3. Okay, so let's go back to our notes. Key attributes. Well, the domain for both graphs was still all real numbers, negative infinity to infinity. The range, looking at the graphs here, the lowest value is negative 3. Here the lowest value is positive 3. So it seems to depend on the k value. So we can say the range, the lowest value is k, and then we go up to infinity. We're still increasing this whole time. Let's do the horizontal asymptote. It's y equals k, so that could be positive 3 or negative 3. End behavior, as x goes to negative infinity, so as we move to the left, f of x goes to whatever your k value was. As we move to the right, so as x goes to positive infinity, f of x goes to infinity, because it just keeps going up. Now let's think about key points. Before we used a y-intercept, so that would still be a key point in both these cases. So before it was 0, 1, and now this plus 3 has moved it up 3 or down 3. So let's add that. A key point would be 0, 1 plus k. So for our two graphs, our key point was 0, 4. For the other one, it was 0, negative 2. then this would be our next key point, an x value of 1. So before, that value was the b value. So it's 1 comma b plus k. So that could be 1 and 2 plus 3, 1 and 2 minus 3. If our b value was something else, like 4, this would have been 4 plus 3 and 4 minus 3. But basically, you are taking your b value and adding or subtracting k based on what it is. Okay, so how does k affect the graph? Well, it shifts it up or down. Up or down k units. So it affects range. It affects the horizontal asymptote. And it affects end behavior. What does it not change? It doesn't really change the domain. It doesn't change increasing, decreasing. But it does change your key points and your y-intercept. So key points are just points that you definitely want to graph if you were doing a rougher sketch. Forgot to say that earlier. But those are 2 points that you would definitely want on your graph. All right. On to the next example. The next example wouldn't upload into this program, so it's not going to look identical to your notes, but it will look similar. So in the tables on the left, first we have a table of y equals 2 to the x. You already have the x values. The y values, if you plug everything in, you get 1/4, 1/2, 1, 2, 4, and 8. So that's for x values -2, -1, 0, 1, 2, 3. The next table, there are different x values. 1, 2, 3, 4, 5, 6. And we have 2 to the x minus 3. When we plug these x values into this equation, we still get 1/4, 1/2, 1, 2, 4, and 8. For the final one, your x values are -3, -2, -1, 0, 1, 2, and your y values are 1/4, 1/2, 1, 2, 4, and 8. And this is for 2 to the x plus 1. So our y values are the same, but what's different is the x values. So if this is the original over here, we can tell these x values have been shifted right 3. So -2 went to 1, -1 moved right to 2, 0 to 3, etc. Over here in this column, we're going from -2 to -3, -1 to -2. We've moved left 1. So looking at our equations, here we have x plus 1, that moved us left 1. X minus 3 moved us right 3. So it does the opposite of what we expect. So for y equals b to the x minus h, this minus h part is moving us left, right. And in the opposite way we would expect. Okay, so you should plot those graphs on the graph paper that you have in your notes. It will look something like this is your original. Let's see. Then right 3 was in blue. So it should look something like that. And we did left 1 in green. So something like this. Okay, so key attributes. The domain is still all real numbers for all 3 of these. The range is the same for all 3 at 0 to infinity. Key points. Well, our original key points were 0, 1, and 1, comma, b, whatever the b value was. Now when we're moving left, right, what's going to change? It's the x values that are going to change. So this would be h comma 1 and 1 comma b minus h. So if we were moving right 3, that means 0, 1 got moved to 3 comma 1. Sorry, this is the original. 0, 1 got moved to 3 comma 1. Or if we went left 1, 0, 1 became negative 1, 1. So key points we'd use if we were doing a quick sketch. All right, increasing, decreasing. These are definitely still increasing. And horizontal asymptote. I'm running out of space. The horizontal asymptote for all of these is y equals 0. The end behavior for all of them is the same. So as x goes to negative infinity, f of x is going to 0. It's our horizontal asymptote. They're all headed to 0. And as x goes to positive infinity, f of x goes to, f of x goes to infinity, because these graphs are all going up towards infinity as we move to the right. Okay, so how does the value of h affect the graph? We already said this, but h moves f of x left or right. H units. Okay, for the next few examples, move on to video 2.